Yeah.
Yeah. Oh, sorry. Can we make a record of your talk?
Absolutely.
Okay. Thank you. Thank you very much. So yeah, it's time for us to start this webinar. We are very happy to have Professor Ankowski to give us a talk about the neutrino accurate neutrino cross sections. It's my great honor to introduce Professor Ankowski. Professor Ankowski received his PhD from the University of Wrocław in 2008 and constantly served as an assistant professor there. And his research focused on the study of nuclear effects in neutrino and electron interactions and their impact on the accelerated neutrino oscillation experiments. Ankowski has made great contributions to the field through his process calculations of neutrino nucleus cross-sections, which has been incorporated into several Monte Carlo neutrino events generators, such as DUNE and Neuro. I think these are very famous packages and softwares for the neutrino communities. Okay, now let's welcome Professor Ankowski's talk. Yeah. Hi.
Thank you so much for the very kind introduction and for the interest in our results. So today I will be talking to you, I will be presenting to you our recent extraction of the argon and the DUNE spectral functions. Our results are presented in those two papers. I will start with an introduction to the physics of neutrino oscillations, focusing on the Deep Underground Neutrino Experiment, DUNE. I will explain you why, for the purpose of precise oscillation analysis, we are particularly interested in precise neutrino cross-sections. Then I will show you what is the current state of art in neutrino interaction simulations, and I will argue that we can greatly benefit in terms of accuracy when we switch to the spectral function approach. In the main part of my talk, I will present the analysis that led to extraction of the spectral functions of argon. And before I start, I would like to ask you to ask questions when you have them. That will allow me for a better contact with you through Zoom. Shortly after neutrino was proposed as a way to save the conservation of energy and angular momentum, this cross-section for neutrinos was calculated in the paper by Beta and Pyers. And the result was so low that they concluded that there's no practically possible way of observing neutrino. It took 2 decades to actually observe neutrinos. That was achieved by Rines and Cohen. And a few years later, we managed to realize there's more than one type of neutrinos. 4 decades later, we managed to detect the third kind of neutrinos, tau neutrinos. And in the meantime, we learned about correct, thanks to the observation of supernova neutrinos from 1987 event, we managed to understand that the standard solar model is correct, and the long-standing problem of the deficit of solar neutrinos was resolved. And on the related note, we learned that neutrinos can oscillate thanks to the results from Super Kamiokande. Right now, we know that there are 3 non-vanishing mixing angles thanks to the result from Kamland, Diabay, Reno, and Doubleshow, which were awarded a breakthrough prize in 2016. This opens an exciting new possibility that neutrinos may significantly contribute to the asymmetry between matter and antimatter in the universe. Shortly after the Big Bang, we know that for every 10 to the 10th particles of antimatter, there were 10 to the 10th plus 1 particle of matter. This tiny imbalance, 10 to the minus 10th, is the very reason that we exist in the universe today. So we are very strongly interested in the origin of this tiny effect. Thanks to the large mixing angles, neutrinos have the potential to give a sizable contribution, and perhaps even the dominant one, to this asymmetry, and they may bring us closer to understanding antimatter asymmetry. One of the goals of the Deep Underground Neutrino Experiment is to determine the delta P parameter, which is a measure of the asymmetry between neutrino and antineutrino oscillations. DUNE will measure with unprecedented precision all oscillation parameters, test the three-flavor framework, perform searches for beyond the standard model, and also measurements of low energy physics, such as measurement of the solar neutrinos, search for the diffuse supernova neutrinos coming from the past supernova explosions. And if we are extremely lucky and there's a supernova explosion during the lifetime of DUNE, we will also measure it with unprecedented precision. Neutrinos are produced in a given flavor, electron, muon, or tau, which is a mixture of mass eigenstates. Every mass eigenstate propagates and attains a different flavor on their way from the near to far detector, and as a consequence, in the far detector, we typically observe a different composition than we started with. So we observe other flavors appearing. In the simplest case, when we deal with only two flavors, the survival probability for neutrinos has this simple expression, which you can see here. It involves only a single mixing angle and a single mass splitting. To determine the size of those parameters, we need to look at the ratio between the observed events and the predicted flux, predicted unoscillated flux in the far detector. From the magnitude of the dip produced by oscillations, we can determine the size of the mixing angle, and from the position in terms of energy, we can deduce the mass splitting between the states. The problem is that, as you can see, to do the oscillation analysis, we need to know neutrino energy. However, we don't know neutrino energy on event-by-event basis. Neutrino beams are produced in a multi-step process. First, we start with a proton beam, which has definite energy. Then protons are led to interact with a graphite or beryllium target. In this process, they produce pions, which then decay, producing a muon beam. As a consequence, we end up with a broad beam, which is ideal to search for example, new physics, to search for oscillations beyond the standard model over a broad kinematic range. However, it is quite problematic from the point of view of precise energy reconstruction because we deal with a very broad kinematics. In long baseline experiments, neutrino interacting with the target, in the case of DUNE argon, typically knocks out some protons or neutrons, may produce some mesons, and obviously produces a charged lepton, which tells us what the neutrino flavor was.
Sorry.
In addition,
sorry, Artur.
Go ahead.
Can you go to the last page?
Sure.
Yeah. So here in this figure, there is a magnetic focusing horn. So
That's
neutrino is neutron. So
yes.
what's this used for?
Yes. That's an excellent question. We use horns to focus pions, which are still charged. So then you can in the past people used so-called natural beams, but then we realized that if you focus your pion beam, you can actually lead to indirectly to focusing of your neutrino beam, and you can obtain much higher intensity. So right now we use, even in the case of DUNE, we will use 3 horns to collimate the beam as much as possible.
Okay,
thank you so much for this excellent question.
Thank you.
So going back to neutrino interaction, so this is a typical event that we expect in our experiments. So if we had at our disposal ideal detectors, and as theorists we can dream about this, the problem of energy reconstruction would be very simple. You just need to add the kinetic energies of your protons and neutrons, because they already exist in the initial state. You need to add the total energies of all the particles that were produced, pions and leptons, and you need to add the kinetic energies of the excitation products. But the problem is that obviously we do not live in an ideal world, and actual detection is quite problematic. So in particular, neutrons are particularly hard to detect in argon. They typically wander around in argon, and they deposit only tiny blips of energy, as you can see from this simulation. So the information that we collect on neutron energy is not sufficient to reconstruct it. We need to add the contribution of neutrons to get the total estimate of the neutrino energy accurately. We need to add it based on what we see in our detector, especially based on the muon scattering angle and its energy, and preferably the full information on the event. To do that, to get the neutrino energy accurately, we need to accurately understand, we need to accurately simulate the contribution of neutrons. That requires very accurate simulations of multiple differential cross-section, at least doubly differential cross-section, because then we would rely on the information on the best known leg of the cross-section, the lepton leg of the cross-section, to determine the contribution of neutrons. So this is something really essential, that we need multiple differential cross-sections for the purpose of oscillation analysis. If we didn't have precise estimate of neutron energy, we would suffer from a smearing, which would produce significant problems for the oscillation analysis. The contribution of neutrons may be 10% at higher energies. In the regime of quasi interactions, for antineutrinos, it may be much larger than that. So as you can see, when we introduce from simulations a large effect, it needs to be done with the highest possible accuracy. Otherwise, we will not succeed in precise analysis, and our oscillation signal may be affected, and also searches for beyond the standard model physics may be not possible. To show you that perhaps more clearly, you can see here the difference between the oscillation probability corresponding to the delta CP minus pi half and pi half. If we smear the signal for minus pi half, it will become very close to the one for pi half, which means that we will lose the sensitivity to the difference between those values. So if we don't control the smearing, the energy smearing in our detectors, we will lose the sensitivity to the main goal of DUNE, and also to the search for physics beyond the standard model. As a concrete example, a few years ago, NOVA, which is a long baseline experiment, announced that they are observing non-maximal mixing. You can see here that while other experiments observed results which are consistent with maximal mixing, NOVA found that the mixing in their experiment is non-maximal. Less than 2 years after announcing this result on a conference, they had to modify it when they realized that their energy reconstruction was not accurate. After updating the analysis, their results became consistent with maximal mixing. Now we can take a look at the spectrum of events before the change and after the change to realize why that happened. You can see here that the latest results have an oscillation dip. That dip was initially smeared out and vanished because they didn't realize that there was some additional smearing that they didn't account for. In the case of DUNE, we are going to be even more sensitive to systematic effects than NOVA because the statistics that DUNE will collect will be much, much higher. So we will be very soon, after the start of the project, after the start of collecting data, we will be very soon sensitive to statistical effects only because we are going to be dealing with a huge statistics of events.
So it seems sorry. So it seems there's one beam in the around 3 GeV. The data divide from the prediction a lot.
Yes.
So what's
yes.
happened to this point?
I'm not part of the collaboration, and unfortunately I cannot answer you. But but you know, with so many beams, it may be that this is just a statistical fluctuation. Probably that's what they would answer. But you know that's just my guess.
So
that's a very interesting question, but unfortunately
it doesn't matter. It doesn't matter. Maybe it is because of the statistic. Yeah.
Maybe there may be also some migration of events, but it's hard to tell. That's interesting that this one been deviates from the prediction so much. I completely agree.
Okay, thank you.
Thank you so much. At the kinematics of long baseline experiments, neutrinos interacting with nucleons can change neutrons to protons or vice versa for antineutrinos when the energy transfer is not too high. When the energy transfer is slightly higher, then they can excite nucleons and produce hadronic resonance, which then de-excites, producing a single pion or perhaps 2 pions. And when the energy transfer is very high, we are dealing with a process which is best described as scattering on individual quarks inside protons and neutrons. This process is called deep inelastic scattering. The problem is that those processes happen not at the level of free protons and neutrons in our detector, but those processes happen in nuclei because of the low cross sections. We absolutely have to use nuclear targets. So we need to account for the smearing introduced by nuclear effects, introduced by the Fermi motion of nucleons and by the energy distribution of protons and neutrons in the initial state. In the case of the total cross sections, here I'm showing you as a concrete example the quasi-elastic one. The difference between the cross sections for medium-sized nuclei such as oxygen and iron is not really significant, as you can see from this figure. Obviously, they differ from the lightest target, deuteron, which is composed of a single proton and single neutron. But in terms of the total cross section, those medium-sized nuclei do not differ that much. The problem is that in the context of energy reconstruction, we are interested in at least double differential cross sections. And here the situation is very different. I would like to illustrate it to you using the cross sections calculated for electrons for different targets. Those calculations we are essentially 100% sure we can verify their accuracy. So I decided to show you those cross sections. For neutrinos, they would be very similar. So in this figure, you can see the double differential cross-section presented as the energy transfer, as function of the energy transfer. So the first structure in this figure is the quasi-elastic peak, the process in which we only knock out, in this case, proton without any associated pion production. So this process corresponds to the delta peak in this figure. Then we have different mechanisms of pion production. First, the delta peak, and then higher resonances produce those two peaks, and then we have a smooth transition to the deep inelastic regime. Now let's take a look how this cross-section changes when we go from hydrogen to deuterium. You can see here that there is already a visible smearing, and the quasi-elastic peak has now a finite width, and all the structures are visibly smeared. Now, when we go to carbon, this is how it looks like. You can see that everything is very substantially smeared. The Fermi motion of nucleons and their energy distribution broadens all the structures. So we end up with essentially the quasi-elastic peak, the delta peak, and after that we have a smooth spectrum corresponding to pion production. We need to account for this smearing in our cross sections in order to reconstruct neutrino energy accurately, and that is the main topic of my presentation today. To show you where we currently stand in Monte Carlo simulations of neutrino cross sections, I would like to refer to the results from the experiment Minerva, which is a dedicated experiment measuring neutrino cross sections in the Fermi lab. A kinematics very similar to that in DUNE. So Minerva finds, for example, in this paper from 2014, that nuclear models available to modern neutrino experiments give similar results, but none of them is confirmed by the data. So more theoretical work is needed to correctly model nuclear effects in the whole regime relevant to oscillation experiments. In one of the latest papers, they use, I would say, a very strong language that improvements will need to be made to neutrino interaction models if precision neutrino oscillation experiments hope to better constrain the systematics. So, this is a very strong motivation to continue the research that we are doing. The good thing about neutrino cross sections for the long baseline program is that interactions with nucleons happen at the level of individual protons and neutrons, at least predominantly. This picture, called the impulse approximation, is valid when the momentum transfer is high enough. I would say around 200 MeV over C or higher. In this regime, to calculate the cross-section for neutrino scattering on a nucleus, we need to know the elementary cross-sections for every channel of interest, so quasi-elastic, resonant pion production, and deep inelastic scattering. And we need to average them over the distribution of the initial proton and neutron momenta and energies. Those distributions are called the spectral functions. And to predict particular final states, we need to account for final state interactions and do the hadronization right. But the good thing is that electrons and neutrinos probe, at least in the impulse approximation.
Sorry, I have a question.
Yes.
And in some calculation, we neglect the final state interaction. What is the impact on the cross section?
So sorry, I didn't let me.
Okay.
Could you repeat your question?
The final state interaction.
Oh yes.
In some calculation, it's be elected.
Yes. In some, yes, you're absolutely right. Yes, in some calculations it's neglected. It depends. So the effect depends. So the effect of final state interactions is model dependent, I would say. So in in the calculations that I will show you in a moment, this effect does not change, for example, the angular distributions. But you will see in a moment that it affects some distributions very strongly. Not the whether or not it affects the total cross sections. That's up to a debate. But so right now, I don't have a definite answer. It depends on a model. In our calculations, it doesn't affect the total cross sections. It doesn't affect the angular distributions, but it is essential to reproduce some cross sections, and you will see that in a moment.
Okay.
That is a very important question. Thank you. Thank you so much for that. So when we calculate the cross sections for nuclei, we need to keep in mind that electrons and neutrinos probe nucleus in a very similar fashion. And that is extremely helpful because it means that we can test the accuracy of our calculations. And we can also take some ingredients from a data-driven approach or from other calculations. So, for example, the spectral functions can very well be measured using electron data, and that will be the main topic of my presentation. We can also take the vector contributions to the elementary cross sections of neutrinos. We can base them on precise electron scattering data for protons and neutrons. We can also learn about hadronization, looking at experimental data for the lightest targets, hydrogen and deuterium. And we can also learn about final state interactions by comparing light targets and the targets that we are interested in. We can use electron scattering data to validate our Monte Carlos and to reduce systematic uncertainties, because we can see some problems and we can remove them. And we can also, in the future, rigorously determine Monte Carlo simulations uncertainties instead of just comparing different simulations and hoping that this is the right estimate of the uncertainty. That was one of the topics of the paper that I recently wrote with Alex Friedland. In this paper, we compared to electron scattering data for various targets. We used the Monte Carlo simulation called the DUNE, which is the most commonly used Monte Carlo generator in the neutrino community. Probably this is the most interesting plot in the context of DUNE. This is the only data set that we have at our disposal for argon. This data set was collected at 2.2 GeV, which corresponds to the peak of the DUNE beam. In this plot, presenting the double differential cross section as a function of the energy that electrons transfer to the argon nucleus, you should be comparing the data with the black line, which shows the total prediction of DUNE. You can see that the first structure in this figure corresponds to the quasi-elastic cross section. So this is the process in which a single proton or a single neutron is knocked out from the nucleus. And that structure in this picture is reproduced quite well by Jiang. But after that, we have a number of problems related to pion production. And this is a serious problem for long baseline experiments. When we lower the beam energy, and here I'm showing you the results for carbon, we can see that there are also problems in the quasi-elastic peak, in addition to the problems in the delta region that we saw before.
So, sorry, this degree is the beam with respected to the target, or
yes? So the scattering angle is the angle that electrons deviated from after the target.
Okay.
So it's the scattering angle of the electron beam.
Electron. Okay, I see.
Yes. In this case, these are electron scattering data. because for them, we know the initial energy, we can measure the final energy, so we have full control over the kinematics, and that is really essential because we know exactly, looking at the data, what happened, and we can tell which process is described wrong. So in this case, for example, looking at the data, we can tell that the quasi-elastic peak is wrong, which tells us that the description of the knockout from the nucleus, this knockout of protons and neutrons, is wrong.
Okay.
In the case of neutrino data, when we collect, when we say that in our detector we have events with no pions, those events can come from the same process, quasi-elastic scattering, but they may also come from different mechanisms of pion production, followed by pion absorption inside the nuclear medium. So so data for neutrinos are much more complex, much more involved, and they are difficult to interpret. So it is much easier to refer to electron scattering data because you can immediately tell what is going on, and you can tell which component of your simulation is wrong. So that's the great feature of electron scattering data.
Okay. Thank you.
Thank you so much.
Yeah.
So looking at those cross sections, we can immediately see that there are problems in the quasi-elastic peak, and those problems tell us that the underlying nuclear model is too simple to be true. So typically in Monte Carlo simulations employed in neutrino community, we use the spectral we use the Fermi gas model. In that model, we treat nucleus as a cube of non-interacting nuclear matter. So this is the picture that describes nucleus. As you can see, well, it's not the first thing that comes to your mind when you think about the nucleus. And we assume in this model that there is a constant binding energy for all nucleons. In the momentum space, that picture becomes more realistic, perhaps, but it's still the same. It's still the same physics. Only it doesn't immediately strike you as unrealistic. In the momentum space, the Fermi gas model would correspond to a fully occupied sphere, occupied up to the maximal momentum called the Fermi moment. When we look at the two-dimensional plane, which shows the recoil momentum and the excitation energy of the residual nucleus, the Fermi gas would be represented as a set of delta functions, the Dirac delta functions located somewhere here. So in this approach, we neglect all the nuances of the shell structure of nuclei and also interactions between nucleons. But what really matters is, does it affect the cross sections? And the answer is yes. As you can see from this picture taken from the paper that I wrote several years ago with Omar Benar and Makoto Sakura. In this picture, I'm comparing for different kinematics, and the first number always gives you the beam energy. So they vary between 200 MeV and 1.6 GeV, and different scattering angles between 13.5 degrees and 60 degrees. You can see here the predictions of the Fermi gas model, represented by this blue dotted line with final state with the spectral function calculations calculated without final state interruptions. This is this violet line, and the full calculations which account for final state interactions represented by the red line. You can see here that when we account for final state interactions in this approach, which does not involve any adjustable parameters, we can reproduce the data quite well. And we always differ quite significantly from the Fermi gas model. You can also see here that there is a contribution missing. In those calculations, we only have the quasi-elastic process, so knockout of individual protons and neutrons, but we didn't include the process of pion production, and that leads to this discrepancy at higher energy transfers. But you could include pion production also in the spectral function approach. There's no problem about that, and I would like to show you now examples for deuteron, the simplest nucleus. So for the time being, please focus on what's on the left. This is an example calculated for deuteron using DUNE. So this is the these are the lines compared with the data collected at 4 GeV. This is the average DUNE energy. You can see here that there's a number of problems. In the quasi-elastic peak, there is an overestimation of the cross section. Then there are different problems in the region where we produce pions through resonance excitation, and then in the deep elastic regime there are also problems. Now, when we switch to the spectral function calculations, those problems essentially disappear. And I also used here the up-to-date approach to pion production. This is the model of Post and Christie. You can see here that there is, let me go back here. You can see here, in addition to the cross sections, also a one-dimensional heat map, which shows you the difference between calculations and data normalized to data. This is a very useful quantity to immediately understand the size of the discrepancy. And you can see here that for the simulations done using Gini, those discrepancies may be at the level of 30–50% in the quasi-elastic peak and in the deep elastic regime. When we switch to the spectral function approach and update the pion production model, those problems essentially disappear. They are only present in the regime where the cross-section is extremely low. And we understand why is that. In those calculations, I wanted to keep the model as simple as possible, so I didn't account for finite state interactions. And you can see that this affects the cross-section regime where it's extremely low. That problem is not relevant for the long baseline program where we want to get the bulk of the cross-section right. So I wanted to keep it simple on purpose. And this produces problems on the other kinematics where it's not relevant for the neutrino program. So now I would like to show you that this is not some nasty example selected with some hidden agenda. This is actually a good representation of what is actually going on in Gini for deuteron, because Gini was not designed to reproduce those light targets. That's one of the problems. But then, if it doesn't reproduce the data for light targets, how can we also trust it for heavier targets? And it turns out that those problems persist also for heavier targets, such as argon. So when you look at the global comparisons here, which use those one-dimensional heat maps, you can see that actually the pattern of discrepancies is very consistent throughout the data. So this picture, which is very clear and easy to understand, is a good representation of what is going on in general with the discrepancies in Gini. And here, what really matters is the region highlighted in green. In this region, we expect to find 95% of DUNE events. You can see that by switching to the spectral function approach and updating the pion production model, we can resolve all those problems in the relevant region. That's the main message of this comparison. So the main obstacle to calculating the cross sections in the spectral function approach for argon was that we didn't have at our disposal the argon spectral function. So the goal of our experiment proposed in 2014 was to provide the experimental input necessary to construct the argon spectral function for protons and for neutrons. And we also wanted to stimulate a number of theoretical developments, such as those related to the description of final state interactions, which are all relevant to accurately estimate the cross sections for DUNE and also for the short baseline program in Fermilab. The main focus of, I would say, the only focus of our experiment is argon. So you may be asking, why did we collect also data for titanium? And the reason for that is that in this type of experiment, coincidence electron scattering, we scatter electrons on argon, and we detect in coincidence the knocked out protons and the scattered electrons. We cannot repeat the same procedure for neutrons because the detection efficiency would be extremely small. So the best thing that we can do is to switch to the mirror nucleus, which is titanium, do the measurement with protons for titanium, and use it as a proxy for what is going on for neutrons in argon. Now I would like to formally define the spectral function. So the proton spectral function describes the probability distribution of removing a proton of a given momentum from the target and leaving the residual nucleus with certain excitation energy. This is a universal property of the nucleus, independent of the type of interaction. Because of that, we can determine it using electron beams, and then use it to calculate accurate cross sections for neutrinos. In this type of experiment, we start with a very well-known beam energy. We scatter electrons and detect their energy after the interaction, and we record only those events which happen to in which we also record a proton in coincidence with electron. Because of that, we measure everything but the final state of the residual nucleus. But from energy and moment conservation, we can reconstruct those quantities. So based on energy and moment conservation, we can determine the recoil momentum of the residual nucleus. We can reconstruct its total energy, and that gives us an information on the excitation energy of the residual nucleus. And when final state interactions do not play an important role, that gives us also information on the initial momentum of the proton. Based on past studies, we knew from the very beginning that we expect to find 70–80% of nucleons in the shell model states. That was the goal of our experiment, to determine this contribution from experimental data. And 20–30% of nucleons are expected to occupy, not to be found in the shell model states, occupied a very broad kinematics. Those nucleons are involved in short-range interactions, and that contribution is easier to determine from theoretical estimates. It would be very impractical to try to find it experimentally, because you would need to search for a very broad kinematics, and you would be dominated by background. So it would be an extremely inefficient process to find it from experiment alone. Our experiment was done in the Thomas Jefferson National Laboratory in Newport News, Virginia, in Hall A, which was designed exactly for the purpose of such experiments. That hall features two huge spectrometers. You can see them here with two human figures added for comparison. You can see these are really enormous machines which allow reconstruct proton and electron energy very accurately. Our experiment was designed to probe essentially the whole kinematics, where we expected to find the shell model states, and we measured some of the region twice to verify our understanding of finite state interactions. When finite state interactions do not play an important role, the coincidence cross-section that we measure can be expressed in the simple form as a product of the elementary cross-section times the spectral function times nuclear transparency. And nuclear transparency accounts for attenuation of protons on their way out of the nucleus. In other words, protons may deviate from where we expect them to be, and we simply lose them. So we need to account for that. To obtain the spectral function, as you can guess from this formula, you need to measure the coincidence cross-section divided by the elementary cross-section for the moving off-shell protons, and divided by nuclear transparency. The mean field part of the spectral function is assumed to have this form. It's a sum over all the occupied states, in which we sum a product of the spectroscopic factor, which is the strength of every orbital, times the wave function in the momentum space. In our calculations, in our estimates, we use the relativistic mean field calculations by Carlotta Giusti, times the energy distribution. In our fits, we use the Maxwell-Boltzmann distribution for the energy distribution. To reduce the number of free parameters in our fits, we use priors from the past experiments to determine the topmost position so to determine the position of the topmost level, we use the information on the mass difference between the argon nucleus and the system of chlorine plus proton plus electron. That gives us the topmost position. And then we use the information from the past experiments which scattered deuteron and also other targets to determine the positions of the next two levels. And in the case of titanium, we managed to determine the next three levels. To determine the corrected part of the spectral function, we use the approach of Cioffi, Deliati, and Simula. In this approach, we treat correlated nucleons as forming quasi-deuteron pairs with the relative momentum distributed as in deuteron. Those pairs have some center of mass motion, which has Gaussian distribution. And when such a pair is broken apart, we end up with two nucleons going essentially in opposite directions. The energy that is released is their kinetic energy plus some threshold, which can be estimated with a good accuracy based on nuclear masses. The final result that we find from our fits differs from the simple estimate by 3.5 MeV. These are the missing energy distributions that we find for argon and titanium. You can see that we are able to parameterize them quite well. And I wanted to show you that when we look at the results obtained with priors and without priors for argon and for titanium, they turn out to be in a very good agreement. So even without the priors, we would essentially obtain the same values, but with larger uncertainties. That confirms that the values that I determined are confirmed by data, which is something very nice. These are the spectroscopic factors that we find. So these are the strengths of every orbital. Let me go briefly over them. It turns out that the correlated part of the spectral function allows us to lower the chi-square per degree of freedom. So this is a component that we are sensitive to, which is as we expect it to be. And we are also sensitive to the difference between the S shells and other shells. And because for the S shells, the momentum distribution does not vanish when we approach the momentum equal to 0, unlike for other shells. So we use priors from the missing momentum analysis to get the final values of spectroscopic factors. And those values are, I would say, in good agreement. This is also encouraging. In our results, argon and titanium turn out to be quite similar, and all data collected at different kinematics are consistent within the uncertainties that we currently have, which is also quite encouraging. Now that we know that that estimates of the energy levels based on past results for deuterium and for other targets are accurate, we can take a look at to what extent the protons in argon are similar to the neutrons in, the protons in titanium are similar to the neutrons in argon. And it turns out that the agreement is at the level of, it's better than 2.2 MeV, which is a suggestion that those two systems are quite similar. Now I would like to show you a comparison to the past results as a way to determine the strengths and weaknesses of our results. I will be showing you the spectral functions represented as occupation probabilities. So I divided the spectroscopic factors by the shell model predictions. In this is a simpler way of showing you results for different orbitals which may be occupied with very different numbers. In the language of the occupation probability, a fully occupied level means the occupation probability of 1, and fully depleted level means the occupation probability of 0. You can see here the results for the 1 F7 halves, 1 D3 halves, 2 S1 half, and the level that was probed most deeply by the deuteron scattering experiments, 1 D5 half. You can see here that our results for the 2S1 half shell is significantly higher than the past extraction. The results for other shells are consistent within the large uncertainties. But the problem is that the 3 topmost shells are distant only by 1.2 MeV, sorry, 1.5 MeV. So this distance is smaller than our resolution, our energy resolution. So it is interesting to take a look also at the sum of the first 3 shells. And it turns out that presented in this way, our result is in better agreement than the individual contributions, and it's because of the 2S1 half shell. So it may very well be, based on what we can see already for titanium, that we are mixing different contributions. When we look at argon, again, and the result for the 2S1 half shell is too high from our extraction than the past results, and the results for the D shells in our results are lower than from the past extractions. When we combine the first 2 shells, which are in this case distant by only 0.5 MeV, our result is in very nice agreement with the past extraction. Unfortunately, we don't have more data to compare to, but if we look in terms of the occupation probability, we can also compare to calcium, keeping in mind that these are slightly different nuclei, so the agreement is not guaranteed. But those, at least the energy levels, become quite similar in those nuclei when we go deeper inside the nucleus. So when we look at the comparison between calcium and argon, it turns out that the combination of the first two shells is in excellent agreement with the past extractions based on electron and proton beams. However, individually, our results differ, and it turns out that that calcium and argon in the past extractions agree better than our results agree with argon, with the past extraction for argon. So it may be that our results mix different shells, and because of that, we can reproduce the mixture of the first two levels for argon and mixture of the first three levels for titanium better than the individual components. And if you look at the 2s1 half shell, the result that we find is higher than the shell model prediction, which tells us very strongly that we are mixing some contributions with the S shell. So there is clearly a way for improvements in the future. We could improve our treatment of final state interactions. We could vary the wave functions to lower the chi-square per degree of freedom. We could improve the treatment of the corrected part of the spectral function, and we could also try to do a fully two-dimensional analysis, because right now we did it in two one-dimensional steps, one in missing energy and one in momentum. So in summary, the success of the long baseline program requires reliable cross-sections, and the spectral function approach is a viable option for such calculations. Today I presented you the first exploratory analysis of the full data set of the JLab experiment, and we found reasonable parameterization of the spectral functions for argon and titanium, which can be used to describe protons and neutrons in argon. Looking at past results from different coincidence experiments, we could see strengths of our results and also its limitations. So looking at individual contributions, we can see that they need to be confirmed by future analysis with improved theoretical ingredients, and that requires a number of theoretical developments. And that was, if you recall, the idea of our experiment, to stimulate theoretical progress as well as provide the spectral functions for protons and neutrons in argon. So already at this stage, we can say that our experiment has managed to complete its mission, and all goals of it has been already achieved. Thank you so much for your attention.
Okay, thank you much. It's very nice talk. Thank you.
Thank you very much.
Okay, so any questions from our audience?
Excuse me. Can I hear? I have a question about if we want to calculate neutrino and neutrino nucleus cross section, but we don't know the nucleus spectral function. Can we replace it with low-n spectral function of nucleus that's similar to its spectral function?
Yes, these are so we published, so we released well, we can release those spectral functions, and you can use them to calculate the neutrino cross sections. But the caveat is that there are still many ingredients which are uncertain. So the spectral functions are the essential ingredient, but they are not sufficient to get all the cross sections. For example, if you want to produce reliable double differential cross sections, you need to account for finite state interactions, and this is something that that requires further work. And also, when you calculate cross sections, you need to assume some axial contribution. That contribution cannot be verified using electron data alone. And because of that, there are still very substantial uncertainties, which are common for all the models that rely on the impulse approximation. So the answer is yes. Those ingredients are available, but there's still more work to be done to calculate the cross sections.
Okay, thanks.
Thank you so much.
Okay.
I have a question in the chat. Is there
Yes.
any indication in your calculations that there is a better choice of target materials? Oh, I cannot answer that question. So this is just yeah. I can answer jokingly. So for theories, because I am a theorist, the ideal target would be deuterium, because then you don't have the problem of nuclear effects. You can just calculate essentially exactly the wave function, and you can use them. That would be a dream come true. Or perhaps helium. That would be really perfect. But the problem is that you cannot do an experiment of this scale using deuterium. That's out of the question. Helium was also not considered because you would need to have extremely low temperatures. So argon is the right balance between what can be done and what theorists would love to have to keep to have everything very simple.
Okay.
So for practical reasons, yeah, you need to use argon, and that was decided a long time ago. We cannot change it, and now we need to do our best to understand those cross sections. Yes. So there's another question. What's the reason for the yes? Let me go back very quickly. That's an excellent question. Why we are limited by the high momentum transfer? Or high enough, I would say, a momentum transfer. So if you look here, those figures are sorted in terms of the momentum transfer. So the highest momentum transfer that we consider here is 450 MeV, and in the paper we have some extra plots if you're interested in given in the supplemental material. And the lowest values that we have here is 143 MeV. That's the momentum transfer corresponding to the quasi-elastic peak. You can see here that we can still reproduce those data quite accurately. And I need to explain what they are. So this part is the actual quasi-elastic peak, but then here those 2 points correspond to a very different mechanism of interaction. This is an excitation of the giant dipole resonance. You can also see it here, for example, as a deviation of those 2 tiny points. And also here, these are like, I'll say 3 points which deviate from the curve. So here you excite the giant dipole resonance. If you go to much lower energy transfers, that will be the dominant mechanism of your interaction. Those two points will become larger than your quasi-elastic contribution. So if you go to very low energy transfers, you need to treat the nucleus as a collective system. You will essentially excite phonons when you interact, and that will be very different from what we assume that you interact with individual protons and neutrons. So this is a limitation of our approach, but luckily for us, that should be a small contribution to the cross section. And the bulk of your cross section can be accurately predicted, assuming that your interactions happen at the level of individual protons and neutrons? This is an excellent question and very important for the cross-section community. Thank you very much for that question.
Okay. Following this question, I think about the target materials. So it seems we have to check or calculate the materials atom by atoms, one by one.
Absolutely.
Yeah. So is there some general framework, and we can do this automatically? Is it possible?
So that's not possible because but perhaps perhaps you don't need to. So it depends on what you need your cross sections for, because if you're interested in the total cross sections and for some constraints on new physics, perhaps the total cross sections are fine.
Yeah.
Then you can take any target, any spectral function, calculate the cross section per nucleon, and you're good, because the differences are really subtle. So in the context of the total cross section, there's essentially no difference between nuclei. If you're interested in double differential cross sections, or perhaps an even more detailed cross section, then this is a real challenge, and so this is why we have it. Yes. So this is why we spend so much time on it. So here in this plot, I'm showing you experimental data, and you can see here carbon and argon. You can see here that in the context of the double differential cross section, you can see a difference between carbon and argon. So this is something that we, when we reconstruct energy, would like to have done properly. In the context of the total cross section, so in other words, when you add all those values together, this cross section is higher here, lower here. In the end, the total is the same, right?
Okay. Oh yes.
But when you need for your task, exactly, when you need the differential, then it's subtle. You need to account for those differences. For every target that you change, you need to do a separate experiment, measure everything. So it's a long process. It takes a lot of effort of many people. The main, obviously, I'm just a theorist, so my task was extremely simple compared to the effort that experimentalists done. This was a real marvel.
Okay. So another question is, suppose we are doing experiments. We use a semiconductor, for example, the germanium, and so is it possible to use this to deal with the neutrino scattering with semiconductor? Or?
Yes. So you could use this formalism. You could do an electron scattering experiment on germanium or any other target, and you could measure the spectral function, and you could repeat everything in this way. But the problem is that when you're thinking about germanium, probably the thing that you have in mind is some low energy interaction, right?
Yes, yes.
And then the impulse approximation will definitely fail. So you need a very different approach, probably based on RPA. So I wouldn't, for that application, I wouldn't use the spectral function because the cross section will not be reliable if your momentum transfer is very low.
Okay, I see. So yeah, I see. So what I'm asking is because we are considering using the germanium as target to detect the neutrinos or the dark matters. And so yes, furthermore, if we change the incident particle to dark matters, so we will have the neutrino backgrounds. And is it possible to use the double differential distributions to distinguish these two kinds of sources?
So in principle, yes. So that's what I would aim for. Aim for. But the problem is that right now, when you look at the current state of art, this is the uncertainties that we have. So if you take it as it is, if you don't want to fix your generator, you need to say that your uncertainties are at the level of 20%, which
20%.
essentially
20%,
I think.
Okay.
Yeah, these are large effects. So if your uncertainties of the cross section of let's say, in your case, the background processing in the oscillation analysis, the signal process is 20%, then probably that kills any effort to search for beyond the standard model physics, right?
Yes.
Because okay, so if you look, let me just joke for a moment. Perhaps this is a new physics signal in electron scattering, right?
Yeah.
And perhaps this is another signal of new physics. So obviously it's not. This is just a problem with the simplicity of the calculations.
Okay.
But we need to. So in the best interest of the community is to push for as precise cross sections as possible, because that affects the searches for the physics beyond the standard model, and it also affects the oscillation analysis. So if we end up with imprecise cross sections, that will affect the physics scope of our experiment.
Okay.
But on the other hand, if we manage to push for precision, if we manage to perform our research and continue our efforts and produce reliable estimates within the standard model, we can then use them to look for deviations, and those deviations will be reliable. That's what has been done in LHC, right?
Yes.
They are pushing for precision. The experimental community supports theories, and that progress is possible. On the other hand, in the neutrino community, there's, I'm sorry to say it, there's very little support by theorists from the experimental community, and we do what we can, but we're not treated as an important part of the community.
Yeah, this seems very different from LHC community. Those guys devote a lot of time and a lot of people to improve the precision calculations. And on the other hand, they're mainly involved the perturbative calculations. They can do it as precise as possible. But I think in neutrino community, the problem is we usually confront the nuclear stuffs. So that's usually difficult to deal with. And
absolutely.
Yes.
Absolutely. I completely agree with you. Yes.
Okay.
So
is it possible, like the lattice, can deal with this nuclear things in the neutrino studies from the first principle?
There are some approaches to do that. However, in my opinion, this is extremely difficult, because at the kinematics that we are interested in, the best the most natural degrees of freedom are nucleons. And
okay.
you start with a nuclear target,
Yeah.
and after the interaction, you have typically a single relativistic particle, or or let's say if you produce some pions, then you may have a few relativistic particles, and a system that is rather non-relativistic, the residual nucleus. So the spectral function which separates those two processes, you treat separately the vertex and the residual nucleus, is, in my opinion, ideal.
Okay.
Obviously, it would be perfect in the future to reproduce, to check the accuracy of our spectral functions and the form factors that we use and so on. So that would be perfect, but I think it's a separate task from what we do. So our task is to produce reliable cross sections with some degree of accuracy, which can be quantified in the shortest amount of time possible, because DUNE is going to collect data quite soon.
Okay.
If we want to do everything perfectly, starting from ab initio, then that may not produce the desired results in the time scale that we need.
Okay.
But
I see. It's difficult. It's difficult job.
Yes,
Yeah.
yes, absolutely.
Yeah.
Yeah, excuse me. I have a very naive question. So in this talk, you mentioned electron scattering and also neutrino scattering. But these two are very different, right? One is charged and massive, and another one is neutral and massless. So how do you compare them for this kind of calculation, and how this factor will be involved or important or not?
Yes, yes, yes. You're absolutely right that these situations are not perfectly identical, but you can account for the differences between neutrinos and electrons. So electrons scatter predominantly on protons, and in the case of neutrinos, depending on the regime that you're interested in, if let's say if you stick to the quasi-elastic regime for the time being, using electrons you probe mostly protons with some contribution of neutrons. Using neutrinos, you probe only neutrons. So this situation is quite different. But if you collect data also for titanium, you will see something that is very close to the situation for neutrons. So, sorry, to the situation for neutrinos, in which you probe neutrons. So if you consider argon and its mirror nucleus, then you get much closer to the situation for neutrinos. Obviously, there are Coulomb corrections because you deal with the charged particle, but those corrections are not huge. So this is an effect that changes the energy at the vertex by a few MeV. So you can also account for that, and there is a framework to do that. So it's not that electron and neutrino interactions are identical. They are absolutely different, as you say. But because we can easily change targets in electron scattering, because we have some experience with positron and electron beams, we know how to introduce corrections for Coulomb effects. We can know how to approximate neutrons with protons in our experiments. So I think we are in a good shape, translating what we know from electrons to neutrinos. Obviously, there is a major problem related to the axial contribution. The axial contribution cannot be determined using electron beams. And this is a major obstacle, I would say. You need to determine it separately. And because of that, there is a good chance that the Deep Underground Neutrino Experiment will also include in its near detector some module with hydrocarbon to get essentially free hydrogen target in the detector, because then you can use it to determine the axial form factors. And that task was recently done by Minerva. This is this is an excellent paper which was recently published in Nature. This idea goes to I would say goes back at several years, and it was proposed by Lou, who is in Oxford, if I recall correctly, and this is something that can be dealt with, but it requires going beyond argon.
Okay,
sorry if
thanks
I
a lot
lost you.
for a detailed explanation. That's very good. Thank you.
Thank you so much. So this is something that we devote lots of thinking to. And sorry if my answer was long, and it reflects the amount of thinking that we spend on this problem. This was an excellent question.
Yeah.
Thank you so much.
I got your point. That's very good. Thanks.
Thank you so much.
Okay. Oh, it's already 4:20. Okay.
I'm sorry.
I'm sorry. No,
I took so
it's
much
cost
of
you
your
too
time.
much time. Okay. I think one last question or one more question. Okay. Seems no more questions. So I think yes, maybe we can finish this talk today. Thank you, Professor Ankowski's nice talk, and we sincerely hope you can visit us at your convenience.
Thank you so much.
And maybe we can find some project to collaborate together.
Perfect.
On the neutrino physics.
That would be perfect. Thank you so much. Thank you very much for your attention. Thank you for interest in what we do, and yes. I'd love to visit you sometime.
Okay. Thank you.
Thank you so much.
A lot. Okay. Thank you. Okay. Bye-bye.